Hello, YouTubers. Welcome back to my channel. This episode is going to continue our exploration of early human evolution, stemming from the other channel videos on myths of ancient cultures. We've been increasingly focusing on the more fringe theories surrounding these ancient myths, and today we're still building on our previous discussions of quantum coherence, recursive geometry, and material materials as we shift towards some truly fantastic claims. As before, these ideas are examined through the same critical scientific lens, asking whether they preserve traces of real cognitive or environmental processes. It's a continuation of the model that we've already built, just applied to the outer edge of this narrative. And so in this episode, we're exploring the fascinating possibility of a hidden or lost planet lurking at the edge of our solar system. Throughout history, various civilizations have hinted at an unknown celestial body influencing Earth's past events. This mysterious object, commonly referred to as Nibiru or Planet X, has long captured human imagination through mythology and ancient astronomy. Modern astronomers, equipped with advanced technology and sophisticated modeling, have begun uncovering scientific evidence that supports these ancient claims. The recent findings suggest the intriguing possibility of an undiscovered planet influencing the structure and evolution of our solar system. Historical records frequently mention this unseen planet, particularly in Mesopotamian texts where Nibiru is depicted as a celestial body with significant influence. In these ancient writings, Nibiru is often associated with periodic upheavals and cosmic interactions that shaped human history. Similarly, Planet X became a term astronomers adopted in modern times, initially used to describe hypothetical celestial bodies causing gravitational anomalies. Despite skepticism, this idea persisted in pop and scientific cultures, encouraging astronomers to scrutinize observational data closely. This ancient and historical curiosity set the stage for contemporary astronomical investigations into unexplained gravitational phenomena in our solar system. Today, science offers compelling support for the existence of such a hidden planet through detailed studies and rigorous simulations. Astronomers have identified unusual orbital patterns amongst trans-Neptunian objects, hinting at gravitational force exerted by an unseen massive body. Recent models suggest that a large planet once inhabited the outer reaches of our solar system, and that potentially influenced events such as the late heavy bombardment period billions of years ago. Observations from telescopes and sophisticated computer simulations increasingly are pointing to the presence of a Neptune-sized planet yet to be discovered. These scientific clues present a credible case that our understanding of the solar system might soon expand to include this elusive lost planet. Scientists studying the solar system have identified structural anomalies that current astronomical models fail to fully explain. According to a report from New Scientist, planetary orbits and positions within the solar system display characteristics inconsistent with standard theories of formation and evolution. These orbital peculiarities suggest influences from unknown gravitational forces, raising questions about potentially missing celestial bodies. The article specifically mentions how such anomalies could be indicative of additional planets existing during the early stages of the solar system. Researchers consider these inconsistencies as evidence warranting further exploration into historical planetary arrangements. The New Scientist article further discusses that early planetary instability likely influenced the solar system's present structure. Observations reveal irregularities, particularly in the spacing between planets and the eccentricities of their orbits, prompting a hypothesis about a lost planet. The best fit explanations offered by researchers involve the existence of an additional large planet similar in size to Uranus or Neptune. This hypothetical planet would have contributed significantly to shaping the final arrangement observed today. Thus, understanding these structural irregularities provides critical insight into the solar system's complex evolutionary history. Astronomical observations presented in the article reinforce the likelihood of a planet's historical removal from our solar system. The researchers assert that such a scenario would account convincingly for both the eccentric orbits and unusual spacing amongst current planets. Specifically, the planet's gravitational interactions could have induced orbital shifts that triggered migrations within planetary orbits. creating lasting structural patterns. These findings encourage ongoing research as efforts aimed at detecting remnants or indicating evidence of this lost celestial body. Conclusively, though, the structural anomalies highlighted here offer compelling scientific support for reconsidering traditional views of planetary system evolution. David Mizrahy's published simulations support the theory that a missing planet explains historical anomalies like the late heavy bombardment. Mizrahy conducted comprehensive computer-based models to investigate the dynamics of our early solar system. His simulations consistently indicated that current models without an additional planet fail to replicate accurately the solar system's structural features. Introducing a hypothetical planet dramatically improved the accuracy of these models, aligning it closely with actual observed orbital data. Mizrahy concluded that a missing planet scenario best accounts for anomalies in both planetary spacing and historical bombardment patterns. In these detailed simulations, Mizrahy identified how an additional large planet would have influenced this historical period. This event is characterized by intense asteroid impacts on planetary bodies approximately 4 billion years ago, lacked a clear explanation in conventional models. According to Mizrahy, the gravitational influence of a lost planet offers the most robust mechanism for explaining the bombardment's sudden onset and intensity. He states the best results occurred when assuming the solar system initially had 5 giant planets, one of which was subsequently ejected. Mizrahy's work significantly strengthens the case for a historically lost planet. These simulations performed by Mizrahy demonstrate that the absence of this extra planet severely limits the explanatory power of existing models. Mizrahy emphasizes how incorporating a 5th giant planet consistently resolves discrepancies between its simulations and astronomical observations. His finding implies a scenario in which this hypothetical planet eventually exited our solar system due to gravitational interactions with other giant planets. Such interactions would have caused instability sufficient to rearrange planetary orbits and remove the planet entirely from our solar system. Mizrahy's conclusions represent a significant advancement in understanding planetary system formation and evolution. A significant 2017 study from Yale University introduced advanced observational methods aimed at locating a potential hidden planet within our solar system. This research utilized innovative techniques to analyze subtle gravitational influences observable in distant celestial bodies. By examining these gravitational effects, they could infer the probable existence of an unseen planetary mass exerting consistent gravitational pull. Yale astronomers also emphasized that this hypothetical planet likely compares in size to a Neptune-based object on observational gravitational characteristics. The methodology developed through this study marks an essential progression in understanding the potential structure of our solar system. Using specifically refined telescopic techniques designed for detecting distant solar system objects, the observations were carried out using large telescopes equipped to capture faint objects in the far reaches of the solar system, allowing detailed orbital mapping. Milena Rice, the lead researcher from Yale, explained that their team specifically focused on analyzing the effects that a missing planet might have on a trans-Neptunian object, or TNOs. The study evaluated TNOs because their distant orbits provided measurable gravitational disruptions that are potentially attributed to an unseen massive body. According to Rice, we employed new observational techniques to improve our sensitivity, specifically searching for objects influenced by an additional Neptune-sized object. The detailed analysis of these distant objects reveals orbital patterns highly suggestive of gravitational interactions with a previously unidentified planetary mass. These precise measurements contribute essential observational support for continuing investigations into the hidden planet theory. This research notably advanced scientific discussion regarding gravitational anomalies in the solar system, indicating the presence of a massive yet undiscovered celestial body. In the research, the astronomers noted that many distant objects exhibited clustering in their orbital paths, an occurrence unlikely without external gravital influence. This clustering behavior strongly aligns with predictions made by planetary dynamic models involving a hidden planet. The observed clustering shows that numerous objects in the outer solar system have similar elliptical orbits tilted in a uniform direction. Such gravitational signatures, as described by Rice and her colleagues, offer concrete observational evidence supporting the hypothesis of a planet beyond Neptune, arguing that such orbital alignments typically arise from shared gravitational forces exerted by sizable planetary masses. As Melania Rice states clearly, we found compelling orbital alignments that point toward a large Neptune-sized planet hidden at the edge of our solar system. These consistent orbital patterns substantially reinforce the evidence of an additional planet shaping the outer solar system. And further evidence from their orbital data shows that these bodies display tilted planes that deviate significantly from those expected if gravitational forces from known planets alone were considered. The consistent and unexplained nature of these orbital tilts suggests the influence of an external planetary mass affecting their trajectories. These anomalies strongly match the theoretical predictions from earlier. Consequently, the findings provide critical support for astronomical models proposing this hidden planet theory. Such research holds considerable implications for fully understanding the structure and evolution of our solar system. Further observational evidence from their orbital data shows that these bodies display tilted orbital planes that deviate significantly from those expected if gravitational forces from known planets alone were considered. The orbital anomalies show remarkable consistency, suggesting a persistent, predictable gravitational source rather than occasional disruptions. An astronomer cited by the New York Post explained, "The gravitational evidence clearly indicates that another large planet is influencing these distant objects' orbital movements. The consistent and unexplained nature of these orbital tilts suggests the influence of an external planetary mass affecting their trajectories. These anomalies strongly match theoretical predictions involving an undiscovered planet orbiting at substantial distances beyond known planetary orbits. Such research holds considerable implications for fully understanding the structure and evolution of our solar system, as astronomers argue these gravitational perturbations remain difficult to attribute to random events or the cumulative effects of known bodies alone. Consequently, ongoing studies seek additional observational data to validate the precise location and characteristics of this hidden planetary body. Such continued research is essential for confirming or disproving the existence of another influential planet historically shaping our solar system." A 2020 report by the New York Post presented research indicating geological patterns across celestial bodies may imply the historical existence of an additional large planet, too. The study analyzed surface characteristics on planetary moons and others, finding patterns of cratering consistent with large-scale gravitational disruptions. Researchers suggest that these patterns result from significant gravitational interactions with previously unknown planets, influencing asteroid trajectories. This planet's gravitational pull would have redirected asteroids, causing unusual geological markings and distinctive cratering patterns that are observable today. The report underscores that such geological evidence supports theories about an additional planetary body that once influenced the solar system's history. So like we saw earlier on Earth, we see the same evidence throughout the solar system. In the article, astronomers highlighted specific moons around Jupiter and Saturn as demonstrating these anomalous geological characteristics. Analysis of cratering patterns on moons like Ganymede and Callisto reveal formations atypical when compared to those created by known gravitational interactions. The researchers noted these anomalies closely align with previous scenarios. As one scientist stated, these geological signatures indicate an interaction with a large planet now absent, altering the asteroid paths dramatically. Such distinctive geological features thus become crucial pieces of this evidence pointing towards a historically present, influential planetary body. The significance of geological evidence from these celestial bodies lies in their preserved records of historical gravitational events. Since planetary surfaces capture the history of asteroid impacts, the anomalies observed directly reflect gravitational influences from an earlier era. The researchers argue these impact records cannot adequately be explained by existing planetary configurations alone. The patterns clearly support the gravitational presence of another large body capable of significantly reshaping asteroid orbits in the past. These geological markers remain valuable indicators for astronomers, indicating the possibility of that other planet previously existing in our solar system. A recent article from Science Alert explored remaining possibilities and regarding where a hidden planet could reside in our solar system. According to current astronomical models, astronomers have ruled out multiple regions, narrowing the search for potential planetary hiding spots. Amongst the detailed observational surveys, astronomers have systematically scanned large segments of the sky, excluding wide areas previously considered possible locations. As these surveys have progressed, they've refined their understanding of gravitational influences, helping isolate smaller specific regions. The reported 2024 paper significantly refines previous orbital predictions using advanced computer simulations employing sophisticated modeling methods designed explicitly to identify precise orbital characteristics. One key researcher explained, "Our advanced simulations strongly suggest a highly inclined orbit, offering a detailed prediction for future observation testing." This refined prediction dramatically enhances astronomers' capabilities to locate the missing planetary body. One scientist notes the missing planet, if it exists, must be hiding in regions of the solar system that remain challenging for our current observational tools. Astronomers pinpointed an orbital region beyond Neptune, describing areas requiring particularly sensitive instruments to detect faint celestial objects. They indicate an orbital zone as the sole plausible hiding place remaining after exhaustive observational eliminations elsewhere. Gravitational anomalies repeatedly direct other researchers to the same distant part of the solar system, an exploration challenge in what was indeed a hidden region of our solar system. Continuing improvements in telescopic sensitivity and observing techniques now make targeted searches in this region increasingly feasible, as this region represents the most promising location for discovering additional planetary body, as advanced telescopic searches and gravitational analysis have significantly constrained the planet's potential orbit. Finally, the authors of this recent paper emphasize the importance of aligning their refined simulation with forthcoming observational campaigns. The specific orbital parameters identified through their simulations form the basis of targeted telescope searches, aiming to confirm or disprove the planet's existence. The precision and confidence obtained from these advanced simulations guide astronomers towards strategically prioritized observational regions. Scientists involved in the study highlighted, "Our modeling provides specific orbital characteristics that significantly increase the likelihood of detecting the planet observationally." As such, this refined simulation approach represents a valuable step forward in resolving the solar system's structural anomalies related to the missing planetary body. One of the articles listed in the bibliography explored astrophysical research that indicates a scenario where a large planet could have escaped the solar system. This theory arose from studies examining historical gravitational instability among planets in our system's early formation stages. Researchers suggest these instabilities likely resulted from interactions between giant planets, causing orbital disruptions severe enough to eject a planet that, according to simulations, could have been sized similar to Uranus or Neptune. Research into young planetary systems throughout the galaxy indicates planetary instability is a common occurrence. Gravitational modeling and observational data from distant star systems have demonstrated that planetary migration and ejections frequently occur following system formation. Astrophysical studies repeatedly show that massive planets influence each other gravitationally, and this sometimes results in drastic orbital changes. Researchers point to observational examples from exoplanetary systems where similar instability-driven planet ejections are already documented. Such evidence underlines the likelihood of similar events having occurred historically within our solar system. Aligning with previous observations, these findings propose a compelling explanation for the solar system's current structure and observed orbital anomalies. Simulations referenced in the article consistently show large-scale planetary instabilities could cause planets to move dramatically from their original positions. Such orbital disturbances often lead to gravitational encounters strong enough to propel the planets completely out of their star systems. Theoretical astrophysicists have confirmed through modeling that this process remains physically plausible under various early solar system conditions. One researcher highlighted, simulations strongly suggest that planetary escape was a likely outcome of past planetary instability in the solar system. These simulations illustrate how easily planets can be permanently displaced from their original orbits under chaotic gravitational conditions, and consistently demonstrate how even minor orbital perturbations can escalate into major planetary rearrangements. Models highlight scenarios where two or more large planets interact gravitationally, generating significant orbital chaos and instability. Simulated interactions often accumulate in the planet's ejection, permanently removing it from the system. Results confirm that instability-driven planetary escapes would, of course, significantly influence the long-term evolution of planetary orbits and system structures. Astrophysicists studying the escape scenario propose that the solar system's historical instability creates long-lasting changes to planetary orbits reflected in current astronomical observations. The accumulation of evidence leads researchers to conclude that a planetary escape event likely played a crucial role in forming today's observed planetary system structure. Continued research in this area helps refine our broader comprehension of a planetary system, both locally and across the galaxy. The concept of Nibiru, or Planet X, often involves cyclical interactions with Earth, potentially triggering significant geological events. Proponents of this theory argue that periodic approaches of this hidden planet could exert strong gravitational forces influencing geological and climate instability. These interactions, according to hypotheses, might cause volcanic eruptions, seismic disturbances, and even pole shifts due to gravitational disruptions. Such catastrophic scenarios align closely with various historical records, as we've discussed, that describe worldwide upheavals and large-scale destructions. While speculative, these cyclical theories continue to intrigue researchers examining Earth's geological past. Supporters of the Nibiru cycle theories frequently reference geological data to illustrate patterns of repeated global cataclysms. Certain geological anomalies, including widespread sediment layers, indicating sudden flooding or volcanic ash deposits spanning continents, are suggested as evidence of periodic disruptions. Advocates claim these findings correspond to the known cycles of approximately 3,600 years, proposed orbital period of Nibiru. Geological and archaeological records showing civilization collapse or abrupt climate change shifts are cited as further validation of the cyclical hypothesis. As such, supporters propose the periodic return of Nibiru as a mechanism underlying historical cycles of global catastrophe. Additionally, gravitational theory underpins the arguments made by those studying Nibiru or Planet X cycles, highlighting the possible astronomical basis of these catastrophic cycles. Planetary science, as we've seen, acknowledges gravitational forces can significantly affect planetary rotation, axial tilt, and orbital paths when celestial bodies approach closely. Such gravitational interactions could potentially alter Earth's rotation, trigger tectonic instability, and disrupt oceanic and atmospheric circulation patterns. Theoretical dating attempts to align these cycles with historical global catastrophe timelines that have been documented across various cultures. Researchers frequently reference ancient texts from civilizations such as the Sumerians, like we've also discussed, the Egyptians, like we are also discussing, and the Maya, which we will future discuss, each describing periodic disruptive events attributed to celestial influences. These historical records provide approximate dates aligning closely with the proposed 3,600-year cycle of Nibiru. Proponents suggest significant historical events such as the collapse of the Bronze Age civilizations around 600 BCE or climate shifts correlate directly with theorized Nibiru passages. This alignment between ancient documentation and modern cyclical theory continues to simulate astronomical and geological dating techniques, further provide scientific support for aligning proposed Nibiru cycles with known periods of global instability. Radiometric dating and ice core analysis used to identify historical geological events reveal intervals of dramatic climate shifts and geological disturbances that are consistent with these cyclical timelines. Researchers utilize these methods to pinpoint exact periods when significant environmental changes occurred, and we aim to match them precisely to the theoretical Nibiru passages. In that way, it validates the theory that a hidden planetary cycle might impact geological history. And finally, current interdisciplinary research efforts integrate astronomical, geological, and archaeological data to refine the theoretical dating of these cycles. Collaborative analysis seeks to establish clear correlations between historical catastrophe periods and proposed planetary encounters. While the debate continues, comprehensive interdisciplinary study remains critical to resolving questions surrounding the hypothetical periodic return of Planet X. And I think some of these studies sound really promising, especially if we can get real observational data. In conclusion, the case for a hidden or lost planet within our solar system rests on a substantial and growing body of multidisciplinary scientific evidence. Gravitational analysis, orbital modeling, geological records, and observational data each contribute to distinct but complementary pieces to a larger puzzle that we're putting together. Across these fields, the data consistently converges towards the same outcome. The structure, movement, and distribution of objects within our solar system aligns the most effectively with a model that includes historical presence of an additional, now missing, and possibly returning planet. This understanding reflects the accumulated results of decades of research, simulation, and observation. It's not just woo. The precise orbital patterns of trans-Neptunian objects, unexplained gravitational influences, distinctive crater distributions on moons, and sudden shifts in planetary trajectories all point towards past events involving large-scale planetary disruption. These signatures are difficult to reconcile under models excluding an additional planet, but they fall naturally into place once its presence and possible ejection and possible return is considered. Equally significant is how closely that the scientific narrative parallels ancient accounts passed down through human history. Civilizations across culture, continents preserved myths of legends of celestial bodies that appeared, disappeared, or returned on cyclical timelines. Stories of global upheavals, catastrophic floods, periods of darkness, or cosmic realignment often featured wandering or disruptive planet at their center. While these accounts vary in detail and interpretation, their core themes align strikingly well with modern planetary migration, instability, and loss. This overlap between ancient narrative and modern science is more than coincidence. Ultimately, the search for a lost planet serves as a powerful example of myths becoming understood through science as researchers use advanced tools and precise models to pursue the same mysteries that ancient observers once encoded in myth. The evidence gathered from across these disciplines and across time points to a clear and compelling conclusion. A hidden or lost planet once shaped the evolution of our solar system. Its influence remains written in the orbits of distant objects, the scars of planetary surfaces, the fragmented echoes of ancient stories, and possibly encoded in our quantum memory. As scientific exploration continues, the search stands as a reminder that the answers to the universe's oldest questions often lie at the intersection of history, observation, and discovery. Well, that wraps it up for today. Thank you for watching, and don't forget to like, subscribe, and ring that bell like the winners that you are. And I will see you next time. Bye!